TRAPPIST-1e. 1. TRAPPIST-1e for 0.7 TRAPPIST-1. TRAPPIST-1e. 2. TRAPPIST-1e. TRAPPIST-12015 TRAPPIST. 20165. 2017222 TRAPPIST-1e. TRAPPIST-1e. 3. TRAPPIST-1e. TRAPPIST-1e 91% 69%. 82%. 249.7 K 23.5 degrees C. TRAPPIST-1e. 4. TRAPPIST-1e. 2018 TRAPPIST-1e. TRAPPIST-1e. 2024 TRAPPIST-1e. 5. TRAPPIST-1e. 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 6. TRAPPIST-1e. 2021 TRAPPIST-1e. TRAPPIST-1e. 7. 20159112 TRAPPIST. 20165. 2017222 TRAPPIST-1e. 2018111 TRAPPIST-1e. 2024 TRAPPIST-1e. 8. TRAPPIST-1e. 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 TRAPPIST-1e is a fascinating exoplanet that has garnered significant attention in the scientific community due to its potential habitability and unique characteristics. Located about 40.7 light-years away from Earth, TRAPPIST-1e is one of 7 Earth-sized planets orbiting the ultracool dwarf star TRAPPIST-1. Its discovery in 2017 marked a significant milestone in the search for potentially habitable worlds beyond our solar system. 1. Historical context and discovery. The TRAPPIST-1 system was first observed using the TRAPPIST telescope in Chile between September and December 2015. Initially, 3 Earth-sized planets were identified, but further observations using the Spitzer Space Telescope revealed a total of 7 planets. TRAPPIST-1e was confirmed on February 22, 2017, and is recognized for its size and position within the habitable zone where conditions for liquid water might exist. 2. Physical characteristics. TRAPPIST-1e has a diameter approximately 91% that of Earth and a mass about 69% of Earth's. Its surface gravity is estimated to be around 82% of Earth's, indicating that it is likely a rocky planet with a solid surface. The planet's equilibrium temperature is estimated to be around 249.7 K-23.5 degrees Celsius, suggesting it could maintain conditions suitable for liquid water under the right atmospheric conditions. 3. Habitability potential. TRAPPIST-1e is located within the habitable zone of its star, which is critical for the potential presence of liquid water. However, there are several caveats. The planet is believed to be tidally locked, meaning one side always faces the star, resulting in extreme temperature differences between the day and night sides. This phenomenon raises questions about the planet's ability to support life, as it could lead to inhospitable conditions on the permanently sunlit side. 4. Atmospheric conditions. Recent studies indicate that TRAPPIST-1e does not possess a hydrogen-dominated atmosphere, which is often associated with inhospitable conditions. Instead, it is more likely to have a compact atmosphere similar to those of terrestrial planets in our solar system. However, there is uncertainty regarding the presence and composition of its atmosphere. A 2024 study suggests that the planet's atmosphere may be stripping away due to its proximity to the star and rapid orbital motion, which could significantly impact its habitability. 5. Future research and observations. The James Webb Space Telescope JWST has been tasked with studying TRAPPIST-1e and its atmosphere to search for biosignatures or signs of life. As one of the most promising candidates for habitability, ongoing observations will be crucial in understanding whether TRAPPIST-1e could support life as we know it. Counterintuitive insights. 1. High density versus atmosphere. TRAPPIST-1e's high density suggests it has a solid, rocky surface, which is typically associated with potentially habitable conditions. However, the lack of a hydrogen-dominated atmosphere contrasts with many exoplanets that have been found to be less dense and more gas-rich, suggesting that density alone is not a definitive indicator of habitability. 2. Tidal locking. While tidal locking is often considered detrimental to habitability due to extreme temperature variations, some models suggest that if TRAPPIST-1e has a sufficient atmosphere, it could redistribute heat across the planet effectively, potentially allowing for habitable conditions despite the tidal locking. 3. Ultracool stars and longevity. The TRAPPIST-1 system orbits an ultracool dwarf star, which, despite its dimness and low energy output, has a significantly longer lifespan than brighter stars like our Sun. This longevity could create a stable environment for life to develop over billions of years, countering the assumption that only stars like the Sun can support habitable planets. For liquid water and atmospheric conditions, the assumption that being in the habitable zone guarantees the presence of liquid water is challenged by the atmospheric conditions of TRAPPIST-1e. Without a suitable atmosphere, even planets in the right temperature range may not be able to retain liquid water, contradicting the simplistic notion that proximity to a star alone determines habitability. In conclusion, while TRAPPIST-1e remains a leading candidate for further exploration in the quest for extraterrestrial life, its potential for habitability is complex and influenced by various factors, including its atmospheric conditions and the nature of its host star. Future research, particularly with advanced telescopes like JWST, will be pivotal in uncovering the mysteries surrounding this intriguing exoplanet. TRAPPIST-1e. TRAPPIST-1e. 1. TRAPPIST-1e. TRAPPIST-1. TRAPPIST-1e. 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 2. TRAPPIST-1e. TRAPPIST-1e. 2024 TRAPPIST-1e. TRAPPIST-1. TRAPPIST-1e. 3. TRAPPIST-1e. 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 4. TRAPPIST-1e. 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 5. TRAPPIST-1e. 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 For valuable points for in-depth analysis and discussion on TRAPPIST-1e. 1. Potential for habitability. TRAPPIST-1e is situated in the habitable zone of its host star TRAPPIST-1, which presents a prime location for the potential existence of liquid water, a key ingredient for life as we know it. Studies have indicated that this planet might have conditions similar to Earth, making it a strong candidate for habitability. However, the presence of liquid water is contingent on several factors, including atmospheric composition and geothermal activity. The planet's proximity and the nature of its orbit, possibly tidal locking, raise questions about temperature regulation and atmospheric retention. Future studies, particularly using the James Webb Space Telescope to analyze its atmosphere for biosignatures, will be crucial in determining whether TRAPPIST-1e could support life. 2. Atmospheric composition and stability. Research has shown that TRAPPIST-1e does not have a hydrogen-dominated atmosphere, which increases its potential for having a more Earth-like atmosphere conducive to supporting life. However, new findings from 2024 suggest that the planet's atmosphere may be undergoing stripping due to its rapid orbital motion and the influence of its parent star. This phenomenon poses significant implications for the planet's long-term habitability. An atmosphere is essential not only for temperature regulation but also for protecting any potential life forms from harmful radiation. The discussion around the atmospheric dynamics of TRAPPIST-1e thus opens avenues for exploring how similar planets might fare in other star systems. 3. Geophysical characteristics. TRAPPIST-1e's physical characteristics, such as its mass density and surface gravity, indicate that it is a rocky planet similar to Earth. With a radius about 91% that of Earth and a mass around 69% of Earth's, TRAPPIST-1e's geophysical properties suggest it could have a solid surface and possibly geological activity. This point invites discussion on the planet's geological history, potential for tectonic movements, and the implications of these factors for a stable climate that could sustain life. Comparative analyses with Earth's geological processes could yield insights into the evolutionary trajectories of terrestrial planets in diverse environments. 4. Future research directions. The TRAPPIST-1 system, particularly TRAPPIST-1e, presents an exciting frontier for astrobiology and exoplanetary research. With ongoing advancements in observational technology, future missions aimed at TRAPPIST-1e will focus on more detailed characterization of its atmosphere, climatic conditions, and surface properties. The implications of these studies are profound, not only for understanding TRAPPIST-1e itself but also for inferring the potential for life in similar systems across the galaxy. Discussions should also consider the broader implications of discovering life elsewhere, including the ethical, philosophical, and practical aspects of interstellar exploration and potential colonization. In summary, TRAPPIST-1e serves as a focal point for multiple discussions spanning habitability, potential atmospheric dynamics, geophysical characteristics, and the future direction of astrobiological research. Each of these points opens pathways for deeper inquiry into not only the specific characteristics of TRAPPIST-1e but also the broader implications for our understanding of life in the universe. 1. The Mars Exploration Program. The exploration of Mars has been a subject of interest for scientists and space enthusiasts alike, especially regarding the potential for past or present life on the planet. NASA's Mars missions, beginning with Mariner 4 in 1965, have progressively unveiled the planet's geology, atmosphere, and potential habitability. The most significant missions include the Viking landers in the 1970s, which conducted experiments to detect life, and more recently, the Mars rovers such as Curiosity and Perseverance that have been analyzing soil samples and searching for signs of ancient microbial life. The ongoing quest for understanding Mars parallels the investigation into TRAPPIST-1e's habitability, as both focus on the potential for life beyond Earth. 2. The search for exoplanets by Kepler Space Telescope. Launched in 2009, the Kepler Space Telescope was pivotal in identifying thousands of exoplanets, many of which are located in their respective stars' habitable zones. This mission has provided crucial data about the characteristics of these planets, including their size, temperature, and distance from their stars. The discoveries made by Kepler, particularly Earth-sized planets in the habitable zones of their stars, have set the stage for future studies of potentially habitable exoplanets like TRAPPIST-1e. The excitement surrounding Kepler's findings mirrors the current scientific enthusiasm regarding TRAPPIST-1e as a candidate for life. 3. The Voyager missions. NASA's Voyager 1 and Voyager 2 spacecraft, launched in 1977, have provided invaluable data on the outer planets of our solar system and beyond. Their journey and the subsequent discoveries about the moons of Jupiter and Saturn, such as Europa and Enceladus, have raised questions about the potential for life in these icy worlds. The findings from Voyager missions highlight the importance of exploring diverse environments for habitability and life, similar to the ongoing research on TRAPPIST-1e, which seeks to understand whether its conditions could support life forms. The legacies of the Voyager missions continue to inspire the search for life in the cosmos and the exploration of exoplanets. Future outlook. Can we live on TRAPPIST-1e? As we look towards the future of humanity's exploration of space, TRAPPIST-1e holds a unique position as one of the most promising candidates for potential human habitation outside our solar system. The planet is part of the TRAPPIST-1 system, which has garnered significant interest due to its Earth-sized planets located within the star's habitable zone. The following sections will outline predictions regarding the future exploration and potential colonization of TRAPPIST-1e. 1. Advancements in space travel technology. Future exploration of TRAPPIST-1e hinges on advancements in space travel technology. Current propulsion systems limit our ability to reach even the nearest stars within a human lifetime. However, The development of innovative propulsion technologies such as nuclear thermal propulsion ion drives or even theoretical concepts like warp drives could significantly reduce travel times. If successful, these technologies may enable spacecraft to reach TRAPPIST-1 within decades rather than centuries. 2. Ongoing research and observations. The James Webb Space Telescope JWST, launched in December 2021, will play a crucial role in our understanding of TRAPPIST-1e. Through detailed analysis of its atmosphere and surface conditions, the JWST will help scientists determine whether TRAPPIST-1e possesses any biosignatures or conditions supportive of life. Future missions may include advanced telescopes and probes designed to gather more comprehensive data on the planet's climate, geology, and potential for liquid water. 3. Terraforming and habitability. If TRAPPIST-1e is found to have a solid surface and some form of atmosphere, discussions on terraforming might emerge. Terraforming involves altering a planet's environment to make it more Earth-like, potentially allowing for human habitation. This could include methods to thicken the atmosphere, increase surface temperatures, or introduce water to the planet. However, the feasibility of such projects is still speculative and would require immense technological advancements and resources. 4. Human colonization efforts. Assuming that TRAPPIST-1e is determined to be habitable, plans for colonization could take shape. Initial missions might focus on sending robotic explorers equipped with AI to conduct in-depth analyses of the planet's surface and atmosphere. Following this, human missions could be launched to establish a permanent presence. These missions would likely start small, focusing on research bases that could evolve into larger colonies over time. 5. Potential challenges. Despite the enthusiasm surrounding TRAPPIST-1e, numerous challenges must be addressed. The planet's potential tidal locking could result in extreme temperature differences between its sunlit and dark sides. Additionally, studies suggest that TRAPPIST-1e may be experiencing atmospheric stripping due to its proximity to its host star, which could undermine its habitability. Understanding these factors will be critical in assessing the long-term viability of human life on TRAPPIST-1e. 6. The role of international collaboration. The exploration and potential colonization of TRAPPIST-1e will likely require international collaboration akin to the partnerships seen in the International Space Station (ISS) program. Countries across the globe will need to pool resources, technology, and expertise to overcome the immense challenges of space travel and extraterrestrial colonization. 7. Ethical considerations. As we consider the possibility of colonizing another planet, ethical questions will arise. The impact on potential indigenous life forms, the preservation of extraterrestrial ecosystems, and the responsibilities of humanity in a new environment must be carefully examined. Future discussions will need to focus on the ethics of space colonization and the frameworks for governance in extraterrestrial settings. 8. Looking ahead. In conclusion, while TRAPPIST-1e presents a tantalizing opportunity for human habitation, significant hurdles remain before we can call it our second home. Advancements in technology, ongoing research, possible terraforming plans, and international collaboration will be essential in shaping the future of interstellar exploration. As we move forward, the dream of living on TRAPPIST-1e may become a reality, but it will require careful planning and consideration of the challenges that lie ahead.